Yeah.
All the other ones that are coming out are equal strength, though, just in those regions.
So the maximum
Oh, is
will
there?
be in the plane perpendicular to the antenna direction.
Yes.
Along the line, they'll get nothing, and then off axis. Not necessarily going to always need to know that it's an electromagnetic wave, although sometimes it is useful. We're going to look at the practical side of this. Oh, and one thing I forgot before I really jump into that, I want to tell you that it is possible to compute the speed of this based on just the properties of electric and magnetic fields. The speed of this wave, if there's nothing in the way, so in a vacuum, first of all, we reserve a special character for that, c. C is the speed of light in a vacuum. We'll switch back to good old v when light actually goes into a material. But the speed of light in nothing can actually be determined as follows. You take your constant that was in every magnetic field equation, multiply it by the constant that in one form or another was in every electric field equation, and take 1 over the square root of that, and you will get the speed of an electromagnetic wave. Now, if you remember, these had some really tantalizing names: permeability of free space, permissivity of free space. Why did they have those names? It's because those constants literally will inform how fast is an electromagnetic wave capable of traveling free space. The value is 3 times 10 to the 8th meters per second. That is the speed of light in a vacuum, and so far as we understand, that's the cosmic speed limit. You can't travel any faster than that, because this is the transmission of information of nothing, right? Electric and magnetic fields, they don't carry any mass, they don't have any inertia, right? There's nothing that prevents this information from getting immediately to its location, except if there's a fundamental limit on information transfer itself. So these charges are moving around, but we don't get the information about that until much later, because the fundamental information has taken time to transit. Okay. Okay. So let's start with our first topic in light. This is going to be polarization. So, for polarization, there's only one thing we care about with the light, and that is the plane in which the electric field oscillates. So in this particular case, for instance, this wave is moving to the right, and the electric field is oscillating up and down in this plane. It's the plane of the board. Okay? So we might represent it like this. The electric field oscillates back and forth in this plane, and then the motion direction is in this direction. So that's a 90-degree angle. Okay? Since the board is vertical, I might call this vertically polarized light, because the plane in which the electric field oscillates is literally vertical relative to the ground. So the electric field is going like this. Okay? That's what this is representing. Okay? So that plane does not necessarily need to be vertically oriented. If I were to take these dipoles and instead slosh them back and forth like this, it would put the wave like this. Okay? So I'm going to try to draw that somehow. Try to draw the perspective. This is still a 90-degree angle. This is the back and forth that the electric field oscillates with. This is called horizontally polarized light. And of course, there's absolutely nothing stopping you from having diagonally polarized light. So the electric field varies like this. Okay? So it is neither dead vertical nor dead horizontal. You can also have diagonally polarized, which is basically, we're going to split up into both horizontal and vertical parts or components. These are all examples of what we call linearly polarized light. And linearly polarized basically because the plane in which the electric field is oscillating at least doesn't evolve with time. You can have lots of other interesting stuff. You can shake your charge like this. Instead of just shaking it vertically and making vertically polarized, or just shaking it horizontally or diagonally, you can go like this. You can imagine what that would do if you did that to a string, right? You make these kind of loops that go like that. You can have circularly polarized light. Okay? There's lots of different things you can do. Okay? I'm going to mostly focus on linearly polarized light. I'll briefly touch upon some of the more complicated things where the way you're shaking the charge is actually evolving with time as well. So you're not just shaking the charge back and forth along a single axis. And by the way, not to leave it out or anything, I also want to talk about unpolarized light. So unpolarized light basically has all of these linear polarizations in completely equal amounts. If it were properly named, it probably should be called all polarized. But I guess the point being is that since it has all polarizations in it, it's not particularly polarized along any plane. It's got equal ingredients of all that. So the light that's coming off this light fixture right now is unpolarized. The way that the light is being generated, the charges in the light fixture are shaking around at pretty much at random, and they're just as likely to create linearly polarized light in any direction. Okay? So once we have established that light can be polarized, we can start manipulating that. So let's do that. So let's talk about a polarizer. This is a device which is commercially manufactured. At one point, I think the patent was held by Kodak, who used it in their polarizer, a Polaroid camera. Okay? And this is the simplest device I can think of to show you how to manipulate polarization. We'll take a look at more complicated ways that this happens in nature. So what do you have? What you have is a material where the atoms are drawn into a very particular configuration. A typical polarizer is made out of these very long string polymers that are pulled into a macroscopic uniform axis to the best extent that they can. And here's what happens. If you were to send a light beam into this, which was horizontally polarized, so what I'm doing is I'm going like this, and I'm sending a beam like this. Well, it turns out that along the axis that these polymers exist, charges can move. Once this electromagnetic field has gotten picked up, charges are actually able to move along this axis accordingly. And the issue is then that they will dissipate this energy to heat. That's what we know charge motion inside something does. So this will actually dissipate the energy out and kill this. So that polarization will not survive passing through this. However, if we send in vertically polarized light like this, well then the charge let's say we have a given charge on one of these tendrils here. Since it can't move up off that tendril, it will just oscillate in place, and that will get passed forward. So basically, the polarizer is going to take certain orientations of electric field and just say, hey, you can pass. I like to think of this as like a light harp, okay? So you guys know how a harp works, right? If these were strings on a harp or a guitar, right, if you want to strum them, ring, you go like that, right? You pluck them like this. You need to pluck transverse to the strings. If you try to pluck a harp like this or a guitar string, they'll just go, and you'll kill the energy to heat, especially on the strings that are scratchy. You'll hear it, okay? So the energy is not transmitted to the environment as much, right? So what we do, so this is like a light harp, and what we do is we label the axis along which this will allow polarization. This is called the transmission axis. Or, as we abbreviate it, TA for short. That is the axis along which polarization will be allowed. I want to point out that it is actually perpendicular to the actual tendrils. A lot of misconception about how this works. People think that this polarization will be allowed because it somehow slips through the cracks or something like that. That's not how it works. Better analogy is like a harp, okay? Not like a cheese grater, okay? And as you can see, these polarizers that I have with me, okay, they are solid pieces of material, okay? There's no gaps here. So what we aim to do is we understand that this particular device, I drew it as a square there, and you can cut it into any shape. Usually the standard shape is a circle. We understand that there will be a transmission axis, and it will allow through 100% of something that's lined up with it, and if something is perpendicular, 0% will come out. Okay? So that is the operation of a polarizer, and then you can probably see where we're going with this. What if it's diagonal relative to the transmission axis? Well, it's going to be a partial, right? So any diagonal polarization can be thought of as a horizontal part, which is and a vertical part, and one of them will be blocked and the other allowed through. Okay? So for instance, if I had something like this, well, that has a component which is vertical, which will be allowed through, and a component that is horizontal that will be blocked. So this is a combination of these two. Okay? So let's see how far we can get with this today, and then we'll pick it up next time. So if I have a polarizer, let's say I have a, let me not put the double-headed arrow on, that's just to represent that it goes back and forth, but if at a particular moment it looks like this, let's call the amplitude E. We can split this up into two components, and E cosine theta is what actually goes through, right? So E cosine theta is the component along the transmission axis, and E sine theta gets blocked, okay? So E sine theta was blocked, okay? So essentially, whatever comes in is reduced by a factor of cosine theta. So you could say that E out is equal to E in cosine theta, where theta is the angle between the incoming polarization and the transmission axis. That's the angle that you should be measuring. You can convince yourself that if the angle is 0, then E out equals E in. It's 100% let through. If the angle is 90, then you get nothing out. And of course, if you're somewhere in between, your amplitude will be reduced, but not entirely reduced to 0. Okay? So, I think that'll have to do it for today, but the thing that I should tell you is that we don't actually observe the electric field by itself. We observe a quantity related to electric field called intensity. So we need to establish what that relationship is so that we can turn this law into something that is useful on the everyday level. Okay, so something that we can compare to observation. Okay, so let's knock off there for today, and we'll pick this up next time.